In section 6.2, we're using proportions to solve geometry problems, so using proportions like we did from yesterday. And expanding a little more on that. First of all, we're looking at different ways to write proportions. So some additional properties of proportions here. We start with our generic if A equals B, or excuse me, if A over B equals C over D, then actually all three of these are true. And these are written as three sort of different theorems in your book. We have three properties. First is called reciprocal property. Now you know that the word reciprocal means flip your fraction around. So if A over B equals C over D, then flip both fractions and do the reciprocal. Then B over A equals D over C. Something to notice, the same numbers are still diagonal. A is still diagonal from D, and B and C are still diagonal. So keep in mind that kind of helps show that they really are the same. Another property is called interchange the means. Well, the means, remember that the means are in these two spots. So we're changing where B and C are. Instead of B being down here, C is. Instead of C being up here, B is. So we flip those around, but notice A and D. Whoops. Notice that A and D stayed in exactly the same place as they were. So we know we can flip-flop the means. Similarly, you could flip-flop the extremes, and that'd be fine. The same numbers are still diagonal from each other. And the last one, a little more work involved to understand why it's true here. All right, this last property is called, well, it's adding the denominator to the numerator. The denominator here was B, so I'm adding that to the top. I'm doing A plus B still over B. Denominator here was D. I'm adding that to the numerator, so I'm doing C plus D still over D. Now, why is this true? Why does this work? Remember how the thing I started with was A over B equals C over D, right? That's the original proportion. Now, we know we can add something on both sides of an equation as long as it's the same. It'll still be an equivalent equation. So I'm going to add 1 on both sides. I hope that you'd agree there's nothing wrong with adding 1 on both sides. There's no problem there because you're adding the same thing on both sides. But what if I change the way that the number 1 was written? Remember our denominator here was B, and I'm trying to add B. So what if instead of 1, I added B over B? Isn't B over B still 1? Anything over itself is 1. And instead of adding 1 here, remember how our denominator was D, and we're supposed to be adding D to the top? What if I add D over D? Anything over itself, again, is still 1. So really, I'm still adding 1 on both sides, and now you know that if you have a similar or like denominator, you add the numerators, keep the denominator the same, so you get A plus B over just B, and C plus D over D. This works because you're just basically adding 1 to both sides and changing the way it's written. So anytime you have a proportion, you can add the denominator to the numerator on both sides, and it'll still be a true proportion. Okay, so 3 properties of proportions: reciprocal property, flip both fractions, interchange the means, which are the diagonal ones here, or add the denominator to the numerator. Let's use those properties here. In this diagram, AB over DE equals AC over DF, write for true proportions. So I'm looking at these two triangles. They look like they are similar. We're going to be talking about similar triangles later this chapter. I'm going to write this proportion just the way I see it, plugging in what I know. So where is A over B? Not A over B, I'm sorry. Where is side AB? Side AB was here, and that's 12. So I'm going to put 12 on top. Over DE, where is side DE? That's this length here, which is 9. Equals, where is AC? I'm going to put that number here. AC, that's a length of 8. Over DF, and DF is labeled as X. I was told to write 4 true proportions. I guess I don't have to solve. I could, right? But there's my first true proportion. I'm going to do this property here, which says reciprocal property. I'm going to flip both fractions, and that'll be a true proportion. Instead of 12 over 9, 9 over 12 equals, instead of 8 over x, I'm going to flip that as well, do the reciprocal, and do x over 8. Let's check and make sure the same things are still diagonal. 12 diagonal from x. Yep. 9 diagonal from 8. Yep. Okay. Next property, remember, was interchange the means, which are the two in the spots diagonal here. So I'm going to keep 12 and x in the same places, but I'm going to change where the 9 and the 8 are. Interchange those means, and I'm going to put 8 down here and 9 up here, but notice the same things are still diagonal. And that last property, add the denominator to the numerator. So in 12 over 9, I'm going to add the denominator. The denominator was 9. I'm going to do 12 plus 9, still over 9, equals, in 8 over x. I'm going to add the denominator up here. The denominator is x. So I'm going to do 8 plus x, still over x, and that would be my last true proportion I'm going to write right now. Although there are still many more you could do, as long as 9 and 8 are still diagonal and 12 and x are still diagonal, there are a few other ways you could write these proportions. Alright. In the diagram, they tell you this proportion is true. I want to find ST and VT. ST is labeled as x here. VT is not currently labeled. I'm going to plug in what I know here so that I can solve. SV, do I know the length of SV? That's right here, and that's a length of 8. VT, where is that? VT is this distance. I'm trying to figure out what to call that because this much is 8, sorry, and the whole length was x. Now wait, if you knew this whole length was, say, 20, how would I figure out VT? You'd say the whole thing is 20 minus this much is 8, and what would be left is 12, right? So you're taking the whole thing x, subtracting 8. So couldn't we call VT x minus 8? So whole thing minus 8, that would be VT, and that's what I'm going to put on the bottom here. And that equals SU. Now SU was a length of 12 over UR. UR here to here is 28. Alright, I want to find ST and VT. So ST was x. When I find x, I will have ST, and then I will find VT by doing that number x minus 8. So let's solve this proportion by cross multiplying. Ooh, when I do 12 times that x minus 8, that x minus 8 is a quantity, so I need to put it in parentheses there. And then I have to do 8 times 28. And get 224. Distribute here. 12x and 12 times a negative 8 would be minus 96. And that equals 224. I'm going to add 96 on both sides. So 224 plus 96 is 320. Sorry about that. And then divide by 12 on both sides. And actually I get 26.6 repeating. But maybe since that's not the best way to write that, 0.6 repeating is what as a fraction? You should know that 0.6 repeating is 2/3 as a fraction. So this is what x is, 26 and 2/3. And actually now x was the length from S to T, so I can say that ST is 26 and 2/3 because ST was the length of x. To find VT, I need to take that whole x, which was 26 and 2/3, subtract 8, and I'm going to get, for VT, 18 and 2/3. 18 and 2/3 adds with the 8 to get my 26 and 2/3, so we're good to go. So setting up a proportion, solving for an unknown there. We're going to talk a little bit about scale models and drawings today and setting up proportions for those. We looked at this a little bit yesterday, but when we talk about a scale model or a scale drawing, it represents an object in real life, and it's the exact same shape, everything is relative, it's in the same proportions, it is similar to the object it represents in real life. And hopefully you can think of some good examples of scale models or scale drawings that you use in real life. We'll talk about these in class. A scale model might be an actual model of a house or a building that was going to be built, an actual 3D thing. Scale drawing, a great example of a scale drawing is a map. We use maps all the time to get from one place to another, look at distances, but those are scale drawings, a two-dimensional thing of what it is in real life. And when you talk about the scale of a model or of a drawing, we're looking at how the dimensions in the drawing or the model are related to the actual dimensions. So notice that your drawing or model number comes first, then the actual dimensions second. Now with these scales, you can have labels or units, and they can be different. It just depends on what you're looking at. So an example where we're looking at scale, it says a blueprint shows a scale drawing of an MP3 player. The diameter of the round button on the blueprint is 0.4 inches. The actual length is 1.6 inches. What's the scale? Alright, so scale is always looking at the drawing or the model compared to real life. The blueprint is 0.4 inches. That's being compared to the actual length is 1.6 inches. What is the scale? Okay, I don't like these decimals at all. I'm not going to leave it as 0.4 to 1.6. That's pretty icky. The best way here to get rid of decimals, I think, is multiply top and bottom by 10, because that'll move the decimal to the right. So 0.4 times 10 would just be 4, moving decimal one spot. 1.6 times 10 would be 16. Hey, and that's real nice. That reduces 4 to 16. This is actually 1 to 4, a way better ratio to talk about here. But when I actually write down the scale, I should put labels, and then I know what I'm talking about here. I'm looking at 1 inch compared to 4 inches. So with scale, if you can avoid decimals and it looks nice, that's the best thing to do. But it's also nice to have a 1 first. So there are different ways you're going to see scale written. This is probably the best way to write in this case. This here's an excellent example. You buy a 3D scale model of the Sears Tower in Chicago. Now the actual building, including the antenna, is 1,703 feet tall. Your model is 29.4 inches tall, total, and the antenna is 4.4 inches. What's the height of the actual antenna? And then, a second part, how many times as tall as your model is the actual building? Alright, we'll deal with the first part where we're trying to find the height of the actual antenna. I know the actual building, including the antenna, so the whole thing, is 1,703 feet tall. And then we start talking about the model. I know my model's 29.4 inches tall total, and the antenna on my model is 4.4 inches. I'm going to go back to blue because I'm looking for the height of the actual antenna. Alright, let's see here. So this blue is actual building. Actual building was 1,703 feet. This was in feet, so I'll just jot a little note up here. Actual building including the antenna. So this is the total height. What is the height of the actual antenna? I don't know. So I'm going to put the antenna number on bottom and just call it X. And again, this will be in feet since this fraction is in feet. Now with this side of the fraction, I'm doing everything with the model. My model was 29.4 inches tall total. This is the total height here, so I'm putting it on top. 29.4. This is in inches, and that should be okay as long as this whole fraction is in inches. This whole fraction will be in feet. The antenna on my model was 4.4 inches. Antenna goes here, 4.4, and yes, that was also in inches. Because the units would cancel here anyway. And now if I cross multiply, I should get the feet on my antenna here. So this is just 29.4x equals, I have to do 1,703 times 4.4. You get 7,493.2, and then divide by 29.4. Here it is, the antenna height is 254 we'll do 2 decimal places, 87 and the real height was in feet. And that's for the antenna. Where's the height of the actual antenna? Here it is. Okay. The next part might actually be the trickiest. How many times as tall as your model is the actual building? How many times as tall? Well, there's an issue. Now the feet and inches thing is a problem. I mean, if I look at, I guess I'll look at total height. My thing was 29.4 inches, right? That's the model. Compared to the actual building being 1,703 feet tall. I'm thinking, oh boy, this is quite the difference. Inches to feet. Well, if I want to go to a conversion here and make these units the same, because I need to know how many times bigger this is compared to here, I need to multiply by conversion. Feet was on bottom, put it on top so it cancels. Inches on top, put it on bottom so that it'll cancel. And I know that there are 12 inches in 1 foot. I'm going to cancel these out because there's one on top and bottom, and multiply across. On top, I just get the 29.4. On bottom, I'm multiplying 1703 by 12 because I'm figuring out how many inches are in the actual Sears Tower. It's 20,436. Now these are both in inches, basically. But I need to know how many times taller this is. Really, I should be flipping this around and do 20,436 inches divided by the height of my model, which was 29.4. How many times bigger is this? Let's see here. Whew. Huge number. It is a decimal, so I'm going to say about. I get 695 times larger. That's how many times greater the actual Sears Tower is than my model. But it kind of makes sense. That's one of the tallest buildings. Obviously, my model didn't even come close. So we're using proportions here to apply to real life. I have one more example of one of the most common scale drawings that you use in real life, which is a map. And anytime you look at a map, you're going to see a scale given to you. Like this says 1 inch on the map means 26 miles in real life if you're actually driving. I want to find the actual distance between two cities if they are 1.25 inches apart on the map. So it's a little more than 1 inch. It's going to be a little more than 26 miles. Set up a proportion here. You know that 1 inch on the map applies to 26 miles real life. Well, then that should be the same ratio as 1.25 inches on the map. How many miles real life? In this case, you notice I'm just doing 1 times x, or x. And I end up doing 26 times 1.25 this way. And I get 32.5. Now this was in miles, actual distance between the cities. So using a scale on a map can be really nice. You just have to actually measure with a ruler and figure out how far apart. But you set a proportion and find that unknown. And that's what we're doing this whole chapter, or whole section, setting up proportions and finding an unknown for a real life problem.